Welcome to Cookie's Maths and Science Hub. Today we're going to explore the periodic table, including many different aspects that we can use to help us in chemistry. The periodic table lists all the elements that we know of, and is a key aspect of scientific understanding. In chemistry, I would go as far to say as it is the most powerful tool in your arsenal for any sort of problem or scenario you may be facing. The first framework for the current modern periodic table was developed in 1869 by Dmitry Mendeleev. It can help identify trends and patterns while also assist in the prediction of reactions and interactions between different chemical groups. When looking at a specific element on the periodic table, there are four key factors to take into account. There is the atomic number, and we'll go through what each of these mean momentarily. The atomic number is the number at the top. You then have the element symbol. You then have the name of the element, and then you have the relative atomic mass of that element. Now, for the last one, sometimes that will vary, and sometimes it will just be the atomic mass or the mass of a specific isotope close to the atomic mass. So just be careful with that one depending on what kind of periodic table you are reading. So, what do each of these things mean? Well, the atomic number is the number of protons an element has, and it is what we use to organize the periodic table. Obviously, as you scroll from left to right and down, it goes from 1 through to about 118 on most periodic tables. If the atom is neutral, it's also the number of electrons present in that atom. As if it's neutral, it has the same number of protons and electrons. The element symbol is the letter or letters that represent the element. Often they are the first letter or two of the element, but sometimes, because these elements were discovered all throughout history, they use older Latin names, so the letters might not always line up. A good example of this is iron, which you would think might be IR, but IR is actually iridium. Iron is represented by Fe, which stands for some Latin word that used to represent the metal of iron. Then you have the element name. That's pretty straightforward. It's just the name of the element. Finally, you have the relative atomic mass. Now, I suggest you check out our video on relative atomic mass if you want some more details. But effectively, in a quick summary, this is the average atomic mass of every isotope of that element, based on their percentage abundance. That is, how much they exist in the real world. Now, as I stated, this can sometimes be swapped out for just atomic mass of a single isotope, and in this case, it usually represents the number of neutrons and protons added together. When reading the periodic table, we need to be careful of how we refer to specific places on the table. So, groups run down, or the columns on the table, are groups, and could be either numbered 1 to 18, which is the whole periodic table, or the Roman numerals 1 to 8. Now, you'll see the Roman numerals skip this middle group, known as the transition metals. We'll talk a bit about them shortly. But effectively, this is because in simpler chemistry, it's good to have those basic 8 groups. Again, we'll talk about this a bit more shortly when we get into some trends. Periods on the periodic table run across, so they are the rows. So as you can see here, we have rows running across, or our periods running across, and our columns running down, or our groups running down. For example, the one I've highlighted here, chromium, we'd go, okay, that's in group 6, because and we use the numbers, not the Roman numerals for this one. And if we look how far it is down, 1, 2, 3, 4, therefore it's in period 4. So it's in group 6, because that's the 6th column going across, and it's in period 4, because that's the 4th row going down. Another important factor of reading the periodic table is understanding metals, nonmetals, and metalloids. This is quite straightforward, as most periodic tables will have what I call the staircase, and is often referred to as such. This line here that looks just like a black thick line indicates that on the left of this line are metals, and on the right-hand side are nonmetals. Now you have to be careful, as I'll show in the next slide, as some are also considered metalloids, which have properties of either. The metalloids, which have some properties of metals and nonmetals, surround the staircase. You'll see it's not everything around the staircase, but most of what is around that staircase where we indicate what is metals and nonmetals are metalloids. Remembering, metals are to the left, nonmetals are to the right, and metalloids form that small group around the staircase. We can break the periodic table down further into what we call families. Now, there are a multitude of families on the periodic table. I'm only going to focus on about 5 in this video, and these 5 will carry you through until towards the end of your college days, covering most of what you'll use the periodic table for. There's the alkali metals on the left-hand side, then we have the alkali earth metals, then the big group in the middle is the transition metals, then you have your halogens on the right-hand side, and noble gases on the far right. The alkali metals in group 1 are highly reactive metals with just a single outer electron, that is, a single valence electron. They readily form +1 ions because they easily lose that outer electron, and they exhibit vigorous reactions with water. You might have seen before sodium reacting with water. If not, I suggest looking up some of these alkali metals and their reactions with water, as they can get quite explosive as you move down the table. The alkali earth metals are in group 2 and are also reactive metals, with 2 outer electrons, forming +2 ions. They are less reactive than their alkali metal counterparts, but are still quite reactive considering other elements on the periodic table. They are known as alkali earth metals as they are often found in the Earth's crust, and they often form essential components of various minerals. The transition metals are important to know where they are, but realistically you won't deal with any of these properties until well into your uni years, as they get quite complex very quickly. They span from groups 3 to 12, and they have diverse properties, forming colourful compounds and displaying various oxidation states. They are known for their conductivity, malleability, and participation in catalytic processes, and they play crucial roles in industrial and biological applications. Most of the known metals that we talk about in everyday life fall into this group because of the vast amount of properties and uses they have within society. Such examples are iron, cobalt, copper, zinc, all those kinds of things. The halogens of group 17 are highly reactive nonmetals that readily form -1 ions. That is, they easily gain an electron, and they exhibit distinct colors and reactivity because of these properties. They are known for their abilities to form salts with metals easily and play an essential role in chemical processes, such as disinfection and organic synthesis. You'll use these very commonly in your labs within high school and college, and they have a vast amount of properties you'll discuss throughout your college years. Noble gases, finally, are in group 18 and are colourless, odourless gases, and the most important part of these is they have full electron shells, meaning they are fully stable and have no interest in reacting at all. They very rarely form compounds under normal conditions, and their unique properties find applications in lighting, cryogenics, and as inert atmospheres in various industries. Because of their non-reactivity, they're really good to use as a closed space where you can do other reactions without worrying about reactions with the atmosphere around it. Perhaps the most common ones on here are helium, which you see in your balloons every day. Well, hopefully not every day, but if you're having a party every day, I suppose. And neon, which you might see in neon lights around your city. As we've discussed, the periodic table provides us with a vast array of information. An important part of this information is the trends that it can show us, showing the differing properties of elements relating to their reactivity, their electron structure, and a vast wide range of different factors as well. Let's explore some of these now. Electrons in the outermost shell of an atom, or the valence shell of an atom, are called valence electrons. Now, the important thing about the periodic table for these is that the number of valence electrons of an atom is equal to the group numeral of that element for the first 20 elements. It gets a bit more confusing after that. But effectively, this is where we use our Roman numerals. So if we were to look at Roman numeral 6, for example, we could look down and go, oxygen and sulfur both have 6 valence electrons. Now, the number of electron shells, on the other hand, that is, how many shells there are of electrons around an atom, is equal to the period of that element. So once again, looking at oxygen, we can say it has 6 valence electrons, and if we go down the rows, remembering periods are our rows, we go 1, 2, oxygen has 2 shells. So it has 2 shells, and its second shell has 6 valence electrons. Whenever you have multiple shells, it assumes the shells before that valence shell are full. So in oxygen, we'd have a shell of 2, then we'd have a shell of 6, which you can see adds up to 8, which is our atomic number, meaning our oxygen atom is neutral. So once again, let's look at another example now. Let's go, group 2, or Roman numeral 2, remember? So we have, calcium, for example. We must know calcium has 2 valence electrons. Now, calcium's in period 4, so it's going to have 4 shells. So we know then it's going to have a shell of 2, 8, 8, 2. If you're still a little bit unsure about that and how the shells work, I suggest checking out our atom video to look more at electron structure. The reactivity of an element is determined by its electron structure. Now, because of the vast differences between metals and non-metals, we're going to look at them slightly separately. Metals become more reactive as you move to the left of the table. This is because metals want to get rid of electrons, and as we move to the left of the table, they have less valence electrons, meaning it's easier for them to get rid of less electrons. Now, metals become more reactive as you move down across the periods. This is because as you move down, we get more shells, correct? As we've just established in our electron trends. So more shells means those outer electrons are further away from our nucleus, which is keeping them in close, meaning it's easier to get rid of those electrons from further away. Think about it this way. If you're holding something and you're holding it at arm's reach, it's going to be harder to hold on to than if you're holding it against your chest. So because they have more shells, those electrons are further away, it's harder to hold on to them, making them more reactive. Non-metals, on the other hand, yes, they still react based on their electrons, but they want to gain electrons, which effectively means the trend for non-metals is reversed. Instead of becoming more reactive to the left, they become more reactive to the right of the table. This is because their valence shells are more full, so it's easier for them to pull in just one electron than multiple electrons. Now they become more reactive as you move up the periods, again, for the opposite reasons. Because they want to pull in electrons, it's much easier when they have less shells. Because if they have less shells, they're going to more easily pull in those electrons. Think about it again. It's easier to grab something that's right in front of you than it is to grab something on the other side of the room. So it's going to be much easier for them to grab electrons when they have less walls or shells between them and the nucleus. These ideas that we've just discussed about reactivity can be really summed up with our atomic radii trends. The atomic radius is defined as 1/2 the distance between the nuclei of identical atoms that are bonded together. And effectively, it allows us to see the size of an atom. The radius of atoms decreases across the groups from left to right. This is because if we have more protons, it's going to pull everything in closer together. So think about it this way. Lithium, for example, on the left-hand side of the table, only has 3 protons, whereas fluorine on the right-hand side of the table has 9 protons. It's going to have much more charge to pull everything in closer together, such as the electrons around the outside. Now, the radius of an atom increases as you travel down the periods. This is because as you move down the periods, there's more shells. More shells, bigger size. Makes pretty clear sense to me. So, remembering it decreases from left to right and increases traveling down. Now, some people find it difficult to do decrease, increase and prefer just increase, increase. So in that case, you'd say it increases from right to left and increases as you move down, or decreases from left to right and decreases as you move up. Whatever works for you to remember those trends. Electronegativity measures an atom's tendency to attract and form bonds with electrons. This property exists due to the electronic configuration of atoms, that is, the positive charge of protons and the negative charge of electrons. Now, again, this relates to the size and structure of the atoms, as that is how the periodic table is set up. So, electronegativity increases across the groups from left to right. This is because as we move to the right-hand side of the periodic table, there's more protons. More protons means it's going to be easier to pull in electrons. Electronegativity decreases as you move down the periods. As the shells get bigger, it's going to be more difficult to pull in electrons as the protons are further away from the outside of the atom. Ionization energy, on the other hand, is the energy required to remove an electron from a neutral atom in its gaseous phase. Conceptually, it's effectively the opposite of electronegativity. The lower the energy is, the more ready the atom becomes a cation. So effectively, this is getting rid of electrons, whereas electronegativity is gaining electrons. So the trend, as you would guess, is pretty much the opposite. Ionization energy increases across the groups from left to right. As you move to the right, it's going to require more energy to get rid of electrons. Ionization energy decreases as you move down the periods. As you move down, your atoms get bigger. It's going to be easier to lose those electrons as they're further away from that central nucleus where the protons are. Now, as I've stated, ionization energy conceptually is different than electronegativity, but you'll notice the trends kind of line up more than you'd think, even though we talked about them being opposite. This is because ionization energy is the energy required to remove an electron. It's not the energy that we lose when we lose an electron, it's the energy required to remove an electron. As such, high ionization energy often goes hand in hand with high electronegativity. Electronegativity, remember, is the tendency of an atom to gain electrons. Therefore, if it has a high tendency to gain electrons, it's going to require a lot of energy to lose electrons, which is our ionization energy. Thanks for watching. Hopefully now you have a good understanding of a vast array of topics relating to the periodic table. Be sure to leave a like and comment for future topics you'd like to see covered. Hopefully, you'll stick around and subscribe to the channel and share it to all your friends. Hope to see you again soon.